Let's get started on part 3, chapter 5. In this chapter, this section is all about subnetting. Very difficult section. In subnetting, we discuss when you divide your network into multiple subnets, how will the network IDs be assigned? But before we talk about subnetting, we should do a review of binary math. And if we look at communications between computers, when computers communicate, one computer can only send a positive or a negative impulse to another computer. Each one of these positive or negative impulses is called a bit, and they're represented as zeros and ones. Zeros are negative impulses and ones are positive impulses. So if one computer can only send positive and negative impulses to the other computer, how can one computer send the number 7 to another computer? And the answer is, when we take 8 of these bits together, that is called a byte. And different combinations of bits represent different values. This combination of bits, 5 negative impulses and 3 positive impulses, equals the number 7. So why does it equal 7? So let's look at binary math. When one computer sends data to another computer, it is going to send 8 bits, and they could be all positive, could be all negative, or this could be a combination. Each one of these 8 bits is a placeholder to represent absence or presence of a value. So, if the first computer sends 7 negative impulses and a positive impulse to the other computer, it is sending the number 1, because 7 zeros and a 1 are equal to 1, because we have 1, 1, no 2s, no 4s, no 8s, no 16s, no 32s, no 64s, and no 128s. Each bit represents absence or presence of a value. Next example. If we have 8 bits, the first 6 bits are all zeros, they're all negative impulses, and then we have a 1 and a 0. That represents the value 2. That's because we have no 1s, we have a 2, no 4s, no 8s, no 16s. Add them up, you get 2. If we take 6 zeros and 2 1s, that's equal to 3, because we have a 1 and a 2. That's equal to 3. If we have 3 7s, that equals 7, because that's a 1 plus a 2 plus a 4, add it up, and that equals 7. If you can understand that 3 1s equals 7, then you understand binary math. A couple other higher bit examples. If we have a 1 followed by 7 zeros, that's 128, because it means we have 128. If we have a 1, 6 zeros, and a 1, that's 129, because we have 128 plus 1. And if all of the bits are set to 1, then that represents the number 255, because you're adding up 128 plus 64 plus 32, 16, 8, 4, 2, and 1. Add them up. That is 255. Recognizing bit patterns, low order and high order bits. These are low order bit patterns. So 2 1s is equal to 3. 3 1s is equal to 7. 4 lower order bits is equal to 15, because that would be a 1 and a 2 and a 4 and an 8. Add them up, you get a 15. Now look at these higher order bits. 2 higher order bits would be 192, because that's 128 plus 64. Then 3 higher order bits would be 224 because it's 128 plus the 64 plus the 32. 4 higher order bits would be 240 because we have 128 plus 64 plus 32 plus 16. So the way one computer can send the number 7 to another computer is that it sends different combinations of positive and negative impulses. Let's now look at what's a packet. A packet is a message which is sent from one computer to the other. And the packet has two components. It has the data, that is to say, what one computer is sending to the other computer, which is the number 7, and it has the header, and that says which computer it's going to. Packet is made up of data and header. So in this diagram, we can see that this computer is sending the number 7 to workstation 1, because the header says it's going to workstation 1. But that's just the way you and I diagram it. Here is how the computers see it. Workstation 1 is being sent the number 7. The 1, workstation 1 is 7 zeros and a 1, or really 7 negative impulses and a positive impulse. And the number 7 is 5 zeros followed by 3 ones. That's how computers communicate in binary. That's the header and that's the data. Now, actually, the header is not just 8 bits. Actually, the header is 32 bits. The TCP/IP bit header has a 32-bit address space, meaning that if the header is going to, if the packet's going to 129.15.2.1, to represent that number requires 32 bits. So TCP/IP is a 32-bit address space. So this shows a packet whereby the number 7, 5 zeros and 3 ones, is being sent to computer 129.15.2.1. TCP/IP has a 32-bit header. So can an octet be 999? No, because if all 8 bits are set to 1, that's equal to 255. 32 bits in a TCP/IP address space or 4 octets. Each octet is represented as 8 bits, an 8-bit pattern for each octet. There's 129, which is 128 plus 1. There's 15, which is 4 zeros and 4 ones. There's 2, which is just a 1 and a 0. And there is 1. Looking at IP addresses in binary. So let's look at IP addresses and subnet mask in decimal and binary. Now, you and I write it out as 131.15.0.129, and we might say that the IP address, the subnet mask, is 255.255.0.0. But here is how the computers see it over the wire. The IP address is this bit pattern of positive and negative impulses. So there's our 131, there's the 15, there's the 0, and there's the 129. And the subnet mask, 255.255, the computer really sees that as a string of 1s and a string of 1s, a string of 0s and a string of 0s. So the subnet mask 255.255 is a 16-bit subnet mask. Let's look at the class A, B, and C networks and the subnet masks for class A, B, and C. A class A subnet mask is 255.0.0.0. We write it as 255, but really the computer sees it as 8 ones and then 24 zeros. So you can have 16 million potential host IDs in a Class A network because it has 24 bits which are dedicated to host ID. Conversely, a Class C subnet mask 255.255.255.0 is a 24-bit subnet mask, and that indicates that 24 bits are used for network ID, so we have a largest number of networks, but only 8 bits are used for host ID, so you can only have 254 hosts in a Class C network. And this bit pattern can be represented as a /8, /16, or /24. So a Class A network, you could say it's 255.0.0.0, or you could say it's 8 ones and 24 zeros, or you could just put /8. /8 means it's an 8-bit subnet mask. /16 is a 16-bit subnet mask, which is Class B, and /24 is a 24-bit subnet mask. Okay, real tricky part right here. Given network 1.0.0.0 with a 8-bit subnet mask, regular Class A subnet mask, what would the IP address be of the first host, of the 254th host, of the 55th, the 56th, the 57th, and the 513th host? Well, I think you can easily see what the IP address of the first host would be. If it's network 1 and it's the first host, it would be 1.0.0.1. And of course, the next one would be .2. And the 254th host would be 1.0.0.254. And the 255th host would be 1.0.0.255. I thought this octet couldn't be 255. No, it's the entire host ID that can't be 255, and this is 3 octets for host ID, so this is okay. And the 256th host, now, would that be 1.0.0.256? Well, no, because there are only 8 bits in an octet, and the highest value you can have is 255. So how do you represent 256? Well, I mean, how do you represent the 256 value? Well, when you get to the highest number that you can have here, which is all ones, which is represented as 255, to represent the next higher value, this octet becomes 0, and then you use the first bit in the next octet. So, the way you would properly represent the 256th host would be 1.0.1.0, because 255 is the highest that this octet can be. So, once it gets to the highest it can be, it resets to 0, and we use the first bit in the next octet. Very tricky to understand. The 257th would be 1.0.1.1. And the 513th would be 1.0.2.1. If you can understand that the 256th host is 1.0.1.0, you're in good shape. And if you don't understand it, most people don't understand this the first time through, but after you go through it a couple times, then you'll get it. Now, back to subnetting. Subnetting is where you are adding a new network. Maybe you're building a new building or a new floor of networks in your building, and you need to assign IP addresses to the computers in the new network or networks without violating the rules of IP addressing. So, you have only one network ID. And the problem is that if you're going to add a second network, 2 networks require 2 network IDs, but we only have 1 network ID. And the solution is subnetting. Here's the situation. We have been assigned network ID 131.15.0.0. It's been assigned to us by the senior network engineer for use in the building that we are networking. And then it's our job to assign the host IDs to each individual workstation. So the host IDs would be 131.15.0.2.0.3.0.4. Standard Class B subnet mask. Fine. Well, then we decide we're going to add another network in our building, or maybe connect a building to it. So the other network we connect, and we hook the computers up, and the question is, what IP addresses are we going to assign to the computers in this network? Now, if I assign this one 131.15.0.5, I can't do that because this is already network 131.15, and I can't have two networks which are which have the same network ID. So can I make it 16? No, I can't make it 16. That's been assigned to somebody else for use in another building. Can I use 14? No. I got to make do with what I have, 131.15. So I got to find a way to make this single network ID into two subnet IDs, and of course this is what subnetting is all about. Problem is we have one network ID and we need a network ID for the additional segment or other segments, and the solution is we use the third octet for subnet ID. When we calculate the new subnet mask, what we're doing is moving the subnet mask one octet to the right and then using the third octet as the subnet identifier. So before subnetting, initially we started out with a subnet mask of 255.255 and network 131.15. And the fourth octet was being used for host ID. We really weren't making much use of the third octet. So if we push the subnet mask one octet to the right, you and I would write it as 255, but really it's pushed 8 bits to the right. Now this third octet can now be used for subnet ID. We'll make it subnet 1 in network 131.15, subnet 1, workstation 1. So what we've done is we've used the third octet to identify this network as network number 1. Now, when we go over to our next network, we will still use 131.15. But since we've pushed the subnet mask over one octet to the right, we now use the third octet over here to identify this as subnet 2. So they're both 131.15, which satisfies our requirements. And then the subnet is defined in the third octet. Now let me slide this down so you can see the other networks. And so here's subnet .1, .2, and this would be our third network, and this would be our fourth network. They all start with 131.15, and the host IDs are .2, .3, .4, etc. But what differentiates them is the third octet is used for subnet ID, and this is what subnetting is all about. The subnetting, you move the subnet mask one octet to the right, and you use the third octet as subnet identifier. And that's a definition of subnetting. Now, when we calculate the new subnet mask, we need to take into consideration the following. What does subnetting do to the number of network IDs? If we're pushing the subnet mask to the right, the reason we're doing it is to increase the number of network IDs. So subnetting increases the network IDs. But what does it do to the host IDs? It decreases the host IDs. So moving the subnet mask to the right reduces the number of bits in the host ID, and it reduces the potential number of host IDs. So the question is, how far to the right should you move the subnet mask? And the answer is far enough to give you sufficient number of subnet IDs, but not so far that it cuts too deeply into the number of host IDs. So before subnetting, in our original example here, we have a Class B subnet mask 255.255 It is a 16-bit subnet mask, and there are 16 bits in the host ID. When we push the subnet mask a full octet to the right, it gave us 8 bits to use for subnet ID, but it really cut into our host ID. Now our host ID is down to 8 bits. If we only push this subnet mask over half of an octet, if we only push it over 4 bits to the right, it will give us additional network IDs, but it won't cut so deeply into our host ID. So if we push the subnet mask over a half of an octet, 4 bits, so there's the original 16 bits, and there's the additional 4 bits, so that would be a 20-bit subnet mask. You can see that just the first 4 bits are being used for subnet ID, and that leaves 12 bits for the host ID. So this would be a subnet mask of 255.255.240 because the subnet mask just comes over half of an octet. Let me back up. When the subnet mask came over a full octet, that was represented as 255, and all 8 bits were used for subnet ID, but it cut into host ID. But if we only push the subnet mask over 4 bits to the right, it still gives us 4 bits with which to assign network ID. It still leaves us 12 bits for host ID, and the new subnet mask is represented as 255.255.240. So, how do you calculate the new subnet mask? 4 steps. 1, determine how many subnets are required. Are you dividing your network into 2 networks, or are you dividing it into 24 different networks? It just depends how much your organization has grown. Then, once you know how many subnets are required, then you determine how many bits are required to represent this number of subnets, convert those bits to high order bits, and convert that to decimal. These steps are on page 243. So let's take an example. Let's say we are adding, we need a total of 15 subnets. It's a lot of growth, a lot of new floors in this building that need networks, and we are going to need 15 subnets. So then we determine how many bits are required to represent that number of subnets, and 4 bits can represent the number 15. And then we convert those bits to high order bits. And we convert that to decimal, and that's the new subnet mask. It's a 4-bit subnet mask. So, to increase the number of network IDs, we move the subnet mask to the right, and that is called subnetting. And this is the end of part 3 of chapter